Okay, so I want to move on now to talk a little bit about unstructured versus structured meshing. And this is one of those practical concepts. Interestingly, I never had anyone really explain to me the difference in my undergraduate and graduate level classes in fine elements. It wasn't until or maybe I just don't recall, but it wasn't until I got to the real world working that had to confront this issue of unstructured versus structured and learned all about that. I knew about unstructured meshing because it's basically very simple. It's what we've been doing. But structured meshing is a whole nother bag, and there's a little bit of art in it, and you have to be really skilled. And once you know this, you can actually look at a mesh and tell whether it's been structured meshed or not. For the unstructured meshing here, it's characterized by no template. So you'll see what that means shortly, but it's basically the mesh is very irregular. Here's a geometry that we show here that we take the geometry and then we fill in. There are algorithms such as the advancing front. There's different types of algorithms and they have different names. But you basically just fill, and it fills along in a path of tetrahedrals. It does comply with curved boundaries. So of course with the tetrahedral geometries and unstructured meshing in general, we can recapture structures very well, at least the geometries and the surfaces. They have the advantage to be more general, okay, so you can apply them to general complex domains. We've seen this in our applications. There are cases where we tried to mesh and it said it could not create a mesh, you need to switch the element type, and it told you to do tetrahedrals. And so we go in there, we define the element type that we wanted to tets, and then we were able to get a mesh. They are more automatic, so you have the reduction of human interaction, which is really nice. In the structured world, you do have a template. Okay, so you actually have to create. Well, I call it. I don't really call it a template. I call it a blocking structure because that's what a lot of the codes refer to it as, blocks, and the mesh lines are aligned with the geometry of the body. So, in other words, you typically lay down your block structure along the geometry. You take the geometry into a lot of consideration as you develop your template or your block, and that tends to make the mesh lines align with the geometry of the body. A structure of the mesh does comply with curved boundaries. A structured mesh does comply with curved boundaries, but that's only because many of these algorithms have advanced projection algorithms, which we will see an example of that. But you are able to comply with curved boundaries. So here are some guidelines on what a good mesh should be. Should be able to resolve the physics, have a reasonable quality so the solver will not fail, so you don't have with those sliver elements. Simplify the geometry based on the physics. So if you can remove some of the features of a mesh, like the really, and say you had a really complex CAD problem, if you can remove some of that detail that still explains what you're after in terms of the problem, that could help. That's going to be helpful in your mesh because you're going to be able to run faster. Be problem specific. So for example, if you're doing an incompressible material, you might have tets versus hexas if you're worried about a lot of volumetric locking, and meet your project requirements. So that means speed. So I have a project, for example, right now, and the sponsor, says you have to simulate 2 seconds of real time, but I have to do this as a dynamic problem. It's an ejection out of an F-35. So the mesh, the problem is going to be a dynamic, explicit dynamic. So I know that my time step is going to be really driven down because my explicit dynamic is only as fast as the smallest element basically controls it. So in this case, our approach is to create a very coarse mesh that meets the problem requirements of 2 seconds, and then start to add detail in and see what kind of run times we can manage with the mesh we have. So that's an example of what that means. So here's a plot that's showing what type of intervention you need to do when creating various sorts of meshes. On this side, we have very little intervention. So that would be creating unstructured TETs or hexes, and you can use software like Abaqus to do that, as we've done in our applications. On the other side, you have codes that need a lot of intervention, very much, and these are creating multi-block structured meshing that create hex elements. Codes that do this are Ansys ICEM CFD and TrueGrid are popular ones. And there's this like middle ground here where it can do like a mix. You can do sort of a structured sweep extrude, so you mesh basically a 2D one surface, and then if you're trying to get a 3D mesh, you basically extrude or extend that out. And Abaqus can do that. It's called a bottom-up meshing technique. And I can post a application that walks you through that. So a little bit about Ansys ICEM CFD. Here we have a geometry, okay, and you can see it's a complex, fairly complex geometry shown here. And what it does is you basically break this up into blocks. And so you can see that you take the geometry in ICE, these are just screenshots, then you create blocks. And so this is actually pretty detailed. You have everything is like a hex, so it has 8 sides, okay. Everything is a hex, so it has 6 sides, but you can stretch it, and they each have vertices. So you can like stretch these things and manually place them in certain spots. You can subdivide them and just sort of manipulate them. Notice here that you have the geometry outline, but the block does not necessarily conform to the geometry. Okay. So what happens is then you do an aligning step, and what that does is project. So there's these, it's basically you create the blocks, and then you project, and what happens is that the face, it's all geometry, it's not really mesh. The geometry of the block structure here would be projected to a surface that you pick. And so you can see you're able to then get these curved surfaces. Once you have these block structure laid out, and you can see that this is a multi-block structure. I'm guessing there's probably around 30 to 40 blocks there. Once you have that set up, you have all the surfaces projected to your geometry, then you convert that to a mesh. So it basically fills in the mesh, and you can see you get a really nice looking mesh there. The advantage, what's the advantage of multi-block structure? Well, one of the biggest things they say is as you do mesh refinement, it's very controlled. So you can subdivide this block into 100 or 1,000 very quickly, and you can maintain good mesh quality. You're sort of guaranteed that. All right, so that's one big reason, as well as the idea of just having hexahedral elements, which are typically more accurate. In my own work, we've been doing this also. It's a big struggle. Here's a very complex block structure mesh of a vertebrae that we did. This took something like a month to create because it has so many different various blocks. And we've done the brain. This took about 2 to 3 months of blocks all throughout in 3D to create that structure, but you can see how nice the quality is inside. This is another muscle that we did the block structure on. One of the things, there are techniques that you can do. So here's some more geometry just showing that. So when you get to be a really awesome block mesher, and like when I see this, I know right away that was block structured meshing, either manually. Sometimes for simple geometries like this, codes have that built in now. But if you ran an automatic mesher, you'd probably get this, okay? And you can see that in these corners where it's trying to fit a square basically into a circular shape, the quality gets really bad, right? And so that's a bad mesh. What you can do is play tricks on, if you arrange your block structure right, and this technique would be called a butterfly, you can create geometry like that. Okay, so you can see that that's done here. This is a little butterfly technique, and I'm going to demonstrate this, how you do it. Butterfly technique, and then they extrude it out. So what you tend to do, if you're a really good block structure mesher, is to you see shapes and you immediately think about blocking techniques. Not really meshing techniques. They're actually blocking techniques that would get you to a good mesh. So you have to be able to take an object visually and sort of break it up in your mind and figure out, oh, okay, I'm gonna use this technique here, and I'll be able to do that. And so it's very organized, and it's a different way of thinking about how you create your meshes. So it's kind of an interesting thing. I always admire when I see a presentation or a talk. And you can, as a modeler, I can totally know when something's been block mesh, because and I realize that took a lot of art, it took a lot of time, and so it deserves some respect, I think. Okay, so up next we're going to I'll just show you some software, the Ansys, of how we go about creating a block structure.